Although graph theory is very pictorial in nature, we can use algebraic concepts like spectra, the eigenvalues and eigenvectors, to talk about them. In this way, spectral graph theory is unreasonably effective at telling us about the graph that we're working with. We hope over the course of this presentation, you'll appreciate this nuance about graph theory. We'll begin with some discussion about the basic tools we use to talk about spectra, introducing the Rayleigh quotient, which we use to prove my favorite theorem from linear algebra, the spectral theorem. After understanding spectra, we want to transform our graph into the Laplacian matrix so we can analyze its eigenvalues. In this session, we'll be showing how you can actually use the eigenvalues to tell whether a graph is connected or not. We'll then move on to some more macro concepts, like the isoperimetric ratio and its generalization, conductance. These metrics are the main objects studied in graph partitioning, one of the major fields of spectral graph theory. And then we'll finally cap off with a little bit about how spectral graph theory got started, and some of the main applications of it used today.
We start our exploration of spectral graph theory with the Rayleigh quotient. The Rayleigh quotient of a vector x with respect to a square matrix M is defined by the given formula. The Rayleigh quotient measures how much a vector is stretched by the matrix normalized by its own length. To provide some intuition on how this works, let's look at a simple example with the following vector x with entries 1, 2, and the matrix M with entries 4, 1, 1, 3. If we work through the calculations for this particular input, we see that the Rayleigh quotient equals 4. Let's work through another example with the following matrix M and vector x. Notice that in this case, x is parametrized by cos t and sin t. This means that the Rayleigh quotient simplifies to the quadratic form. In this example, the Rayleigh quotient evaluates to 5 plus sine 2t. As you may have noticed with this example, when the vector x is a unit vector, the Rayleigh quotient is always equivalent to the quadratic form. One important property of the Rayleigh quotient is that it is homogeneous. If we scale our vector x by some non-zero scalar alpha, we can factor out alpha squared in both the numerator and the denominator, and our equation simplifies to the definition of the Rayleigh quotient. So no matter how we scale x, the Rayleigh quotient remains the same. It only depends on the direction of x, not its length. Another important property of the Rayleigh quotient is its relation to eigenvectors and eigenvalues. When x is an eigenvector of M, the matrix vector product simplifies to multiplying by a scalar eigenvalue lambda. Because lambda is constant, we can factor it out, and our Rayleigh quotient in the end is simply the value lambda. We can use the Rayleigh quotient along with some of these properties to prove the spectral theorem. The spectral theorem states for any real symmetric matrix M of size n, we can find a set of eigenvalues and corresponding orthonormal eigenvectors such that when these vectors are transformed by the matrix M, they are simply scaled by their associated eigenvalue. Ultimately, this means that the matrix M behaves predictably in the directions defined by these vectors. Those of you who are familiar with matrix diagonalization may recognize the spectral theorem as the fundamental tool that enables us to conduct singular value decomposition. We define the first eigenvector as the eigenvector that maximizes the Rayleigh quotient. Since the Rayleigh quotient is homogeneous, as we showed earlier, we only need to consider unit vectors x. Notice how we use the notation psi sub 1 to denote the eigenvector corresponding to the largest eigenvalue. Subsequent eigenvectors are determined by maximizing the Rayleigh quotient while ensuring orthogonality to all previous found eigenvectors. These properties ensure that the eigenvectors are not only scaled but also orthogonal to one another. As you may have noticed, this theorem lends itself to induction. The base case is that we can construct the first eigenvalue with a non-zero vector x that maximizes the Rayleigh quotient with respect to m. The inductive step is that we can construct the k plus first eigenvector given the first k eigenvectors and eigenvalues, while ensuring that the k plus first eigenvector is orthogonal to all of the previous k eigenvectors. We start with the base case. If x is a non-zero vector that maximizes the Rayleigh quotient with respect to m, then the gradient of the Rayleigh quotient must be 0 at this point. So we can use the quotient rule and set the numerator equal to 0. As you may have noticed, this last equation indicates that the Rayleigh quotient is equal to the largest eigenvalue. This is only the case if and only if x is an eigenvector of m. It may be helpful to keep these steps in mind as we complete the inductive step, since we will refer back to this logic as we will try to work out the inductive case. With the base case now completed, we can move on to the inductive step. In order to prove the inductive step, we will first reduce this problem to positive definite matrices, since positive definite matrices have positive eigenvalues and other properties that make this proof easier. Similar to how we label the largest eigenvalue mu sub 1, we label the smallest eigenvalue mu sub n, and is defined by the given formula. Again, since we are only concerned with unit vectors, the denominator of the Rayleigh quotient simplifies to 1. Since we are denoting mu sub n with the smallest eigenvalue, we know that this must be less than the quadratic form. We know that such an eigenvalue must exist by the same steps that we used in proving the base case. We can now show that solving this problem on M is equivalent to solving this problem on a positive definite matrix. We define a matrix M sub f by the following, essentially shifting each eigenvalue by up to mu sub n. For all unit vectors x, we can multiply through by x transpose x, and the same equation will hold. Now, since we know that the quadratic form must be greater than mu sub n, we can create the following inequality, which reduces to 1. Therefore, M sub f is a positive definite matrix, and since its eigenvectors are the same as those of the matrix M, we can assume that without loss of generality, M is positive definite. We now construct a matrix M sub k, which is defined as follows. Intuitively, you can think of this as removing all of the information of the first k eigenvectors that is encoded in our matrix M. For all j less than or equal to k, we can now multiply by the jth eigenvector. Since the first k eigenvectors are orthonormal, the summation simplifies to the product of the jth eigenvector and the jth eigenvalue, which means that the equation equals 0. This shows that all of our k eigenvectors are in the null space of M sub k. We still need to derive a new eigenvector y that represents the k plus first eigenvector and is orthogonal to the remaining eigenvectors. Now, we seek to maximize the Rayleigh quotient M sub k with the new vector y. To ensure orthogonality, we project y onto the subspace spanned by our established eigenvectors, and we define this projection of y as follows. To verify that it is truly orthogonal, we can multiply this projection by any of our k eigenvectors, and see that since these k eigenvectors are orthogonal to each other, multiplying y sub p with any of these eigenvectors results in 0, proving that if we normalize y sub p, we can get a new k plus first eigenvector. With this proof, we have now proven both the base case and the inductive step, essentially proving the spectral theorem.
The Laplacian is going to be defined as the degree matrix minus the adjacency matrix, where the degree matrix is just going to be a diagonal matrix of all the degrees of your vertices, and the adjacency matrix is just going to be representing all the different edges of your graph. Here we have a basic example. We have our degree matrix subtracted by our adjacency matrix to get our Laplacian, and notice that all the rows and columns sum up to 0. Echoing Arjan's section about the Rayleigh quotient, we can actually define something called the Laplacian quadratic form, where we're really considering a vector as a function on the vertices of the graph, where each component of the vector corresponds to the enumerated vertices of our graph. So this kind of represents the flow of the graph and the smoothness of our vector. So it's only really small if the function doesn't change much over any edge. And we can kind of see this by when we actually take the sum, we're actually finding the deltas between every vertex on the graph. There must be some reason this is called the Laplacian. Now that we have a matrix representing our graph, we probably want to use the eigenvalues of the matrix to say something about the graph. It turns out if we look at the second smallest eigenvalue, or Laplacian, we can actually see whether our graph is connected or not. Let's prove it. So consider when G is not connected. If G is not connected, we can split up the vertices and get G1 and G2 as two different components of the graph. And then we can compute the Laplacian on each component and then bring them together to get the actual Laplacian for G. As an aside, this is in block matrix format. That means that L1, L2 are matrices, and so are the bold zeros. Those are the zero matrices. This is just a more convenient form to show the matrix, and it also makes it easy to show any eigenvectors because those will be in block format as well. You can notice that the Laplacian has two orthogonal eigenvectors of eigenvalue 0. And we can see this by going back to the block representation of our matrix here. Here we're taking the dot product with the block matrix format. And through some algebraic manipulation, we can see that we need that L1.E and L2.F need to be 0 to get eigenvalue 0. And we know that the Laplacian times any constant vector gives you the 0 vector because we noticed earlier that if you sum up the rows or columns, you get back 0. Returning back to the lemma we were trying to prove, we can see that we've actually proven the counterpositive of the forward case. Now we just have to prove the backwards case. All right, for the backwards part of the proof, we want to show that if G is connected, then lambda 2 is greater than 0. So assume G is connected. Let phi be an eigenvector of our Laplacian of eigenvalue 0. We can use the alternate definition of our Laplacian to think about all the different edges of our graph. Here we can see that phi of A equals phi of B for any two vertices. Therefore, phi is constant on any two connected vertices. We're going to exploit this inductively. We know that G is connected, so every pair of vertices A and B are connected by a path. Therefore, we can have a chain of equalities to show that for any two A and B vertices in our graph, we have phi of A equals phi of B. This means that phi must be a constant vector on every vertex, and the eigenspace of eigenvalue 0 must have dimension 1, i.e. there's only one eigenvector of eigenvalue 0. We have just shown if G is connected, then lambda 2 is greater than 0. So we completed the backwards part of the proof and therefore proven the entire lemma.
Another important concept in spectral graph theory is the isoperimetric ratio. The isoperimetric ratio, defined on a subset of vertices, is the ratio of boundary edges to the cardinality of the subset. Boundary edges are edges that connect nodes inside the subset to nodes outside the subset. Note that we denote the boundary edges of a set S with the partial symbol of S. In this case, we get an isoperimetric ratio of 2. We can also define the isoperimetric ratio over a graph G as the minimum isoperimetric ratio over all subsets with cardinality less than n divided by 2, where n is the number of vertices in the graph. We can think of this as taking a single graph G, selecting some subset of vertices S, and calculating the isoperimetric ratio over and over again. Once we have the isoperimetric ratio across all of our subsets, we then sort these ratios to find the minimum isoperimetric ratio. With this graph, the minimum isoperimetric ratio is 0.5, with this subset of vertices S selected. The significance of the isoperimetric ratio is tied to the connectivity of the graph. A large isoperimetric ratio generally indicates a high degree of connectivity between vertices, suggesting that even when choosing a minimum boundary for a subset, there are still many connections or edges that can be traversed. Conversely, a low isoperimetric ratio signifies a weaker degree of connectivity, implying that the selected subset S is more isolated, as we can see in this graph shown.
Earlier we saw that lambda 2 determines whether the graph was connected or not. Here we'll see that lambda 2 actually provides a lower bound for our isoperimetric ratio. This kind of should make sense because we know that a high isometric ratio means that the graph is well connected. So if lambda 2 is big, then our graph is very well connected. Let's see an example of this. Here we have a graph where lambda 2 starts off at 0 and our isoperimetric ratio is pretty low right now. But as we add edges to our graph, our isoperimetric ratio increases and so does lambda 2 along with it. Let's prove it. We'll start off with the definition of lambda 2 as the minimum of this Rayleigh quotient here. Notice that we need x to be orthogonal to our constant eigenvector in order to not get lambda 1, the trivial 0 eigenvalue. Using this definition, we can see that for every x orthogonal to our constant eigenvector, we know that this inequality holds. We already got lambda 2 on the right-hand side, so let's focus on the left-hand side and if we can get something related to our subset, using the vector x. We'll first consider the indicator function of our subset, where it's 1 if our vertex is in our subset and 0 otherwise. We can draw this out and get a better visual of what's going on here. When we evaluate the right-hand side, we see that it's really measuring all the edges that cross the boundary of our subset. And this is a nice result, which connects the Laplacian to the boundary of our subset. However, hold up. Remember earlier, when we had to make sure that x was orthogonal to our constant eigenvector? Well, our indicator function dotted with our constant eigenvector is not equal to 0. i.e. it's not orthogonal. So we need to change up our indicator function a little bit. We can do this with a sort of Gram-Schmidt method where we subtract by a constant vector. In this case, negative s. We're basically shifting all the values of the vertices down by negative s, and we're still maintaining that delta of 1 on each of the edges that cross the boundary of our subset. And let's just check that this is orthogonal. So now we can go back to our example and evaluate using our new x vector. And we can see that this actually turns out to be, as we suspected, the exact same as our indicator function. And it will still give us the boundary of S. Now we can replace the left-hand side with the size of the boundary of S. And we can see that our choice of x gives us x transpose x equaling the size of the subset times 1 minus s. And dividing out by the size of our subset, we get the isoperimetric ratio, thus solving the theorem.
Similar to the isoperimetric ratio, we define the conductance on a weighted graph and a subset of vertices as follows. We denote the degree of a weighted graph V with dV and the sum of the weights of a set of edges F with WF. Recall that the degree of a vertex in a weighted graph is the sum of the weights of the edges incident to that vertex. As an example, consider the graph shown. In this case, the specific graph with a selected subset of vertices S has an isoperimetric ratio of 0.95. The conductance on a weighted graph is then defined as the minimum conductance of any subset of the vertices in the graph. This would look like taking a weighted graph, selecting a subset of vertices from the graph, and calculating the conductance for that specific subset. Once we have the conductance values across all of these subsets of vertices, we then order these values and find the minimum conductance. With this particular graph, the conductance of the graph is 0.26 and includes this subset of vertices S. Just like the isoperimetric ratio, a higher conductance value indicates a stronger connectivity between vertices in a graph, and a lower conductance value indicates a weaker connectivity. Usually, when we are concerned with understanding the edges in a graph, the conductance proves to be a better measure than the isoperimetric ratio.
It turns out we can naturally talk about conductance in this Rayleigh quotient form. This looks a little off. We have this degree matrix at the denominator right here. So let's make a change of variables. And now we're left with something that looks like the Rayleigh quotient that we're used to, except we have this matrix, this weird degree matrix times the Laplacian times the degree matrix again. And we'll call this matrix the normalized Laplacian. Let's look at the eigenvalues of our normalized Laplacian. Like the Laplacian, the normalized Laplacian has a zero eigenvector, and the corresponding eigenvector is d to the 1/2, which is the square root of the degree vector. Basically, the square root of all the degrees of our graph. Similar to the Laplacian, we can see that the eigenvector of the second smallest eigenvalue, mu2, is given by the argmin of this Rayleigh quotient. This is exactly how we define the corresponding eigenvector for lambda2 for our Laplacian. Knowing the backwards formulation of our change of variables, we can go back to y and use what we had initially to find mu2. Like how we used lambda2 with the Laplacian to find a lower bound for our isoperimetric ratio, we can use mu2 to also show a lower bound for conductance. We'll be using this definition of conductance throughout the proof. Like with the Laplacian, let's use the indicator function of our subset as a test vector. We can notice that it's not orthogonal to D, so we'll have to use the same trick with the Gram-Schmidt type process. Here we have to subtract by the constant sigma instead of S. And now let's just check orthogonality. And we get 0, so we're good. We can use the same reasoning from before to see that the numerator of our quotient is the boundary of our subset. Now we just have to compute the denominator. And we expanded it out here. And rearranging terms, we get this formulation. Now we've shown that mu2 is a lower bound for the conductance, proving the lemma.
In general, since the concepts and proofs that we've explored today may seem quite theoretical, we would like to provide some motivation for understanding how and why these concepts are actually applicable. Some of these concepts actually contribute to the mathematical foundation for solving real-world problems in network science and data analysis. One key application is in community detection within large networks. For example, the eigenvalues of the Laplacian matrix help identify clusters in social networks, where groups of nodes are densely connected to each other but sparsely connected to the rest of the network. The second smallest eigenvalue gives us insight into the best way to divide a graph into two connected components. This leads directly to the concept of conductance and the isoperimetric ratio, which measure how well a graph can be partitioned. These ideas are crucial in identifying bottlenecks in communication networks or traffic flow in urban planning. In web search algorithms like Google's PageRank, such metrics help optimize search results by ranking the importance of web pages through graph traversal. Spectral graph theory also isn't limited to computer science or networks. In physics, measures like conductance can help determine how heat will dissipate on a surface. We can model the surface as a graph, with weights corresponding to proportional likelihood of heat transfer between 2 points on the surface. With this graph, the second eigenvalue can tell us how quickly the heat will spread and also indicate regions of potential bottlenecks or hotspots. Ultimately, spectral graph theory provides an elegant framework for analyzing some of these problems, and we hope that with this presentation you are able to learn how concepts from algebra and graph theory can be synthesized to form the foundation of spectral graph theory.